Mastering deep learning. RNNs unlock secrets in sequential data, fueling AI breakthroughs. When a deep learning model is designed to handle sequential data or temporal relationships, what is a recurrent neural network, RNN, and how is it used to process and analyze this type of data in applications such as natural language processing, speech recognition, and time series forecasting? A recurrent neural network, RNN, is a type of deep learning model specifically designed to handle sequential data or temporal relationships. Unlike traditional feed-forward neural networks, RNNs are capable of processing input sequences of varying lengths and capturing complex patterns and relationships that exist across time or sequence. At its core, an RNN consists of a recurrent layer that takes an input sequence and outputs a corresponding sequence of hidden states. This is achieved through the use of recurrent connections, which allow the hidden states to persist across time steps, allowing the network to maintain a sense of context and memory. The fundamental component of an RNN is the recurrent cell, which is responsible for processing the input sequence and updating the hidden state. The recurrent cell takes three inputs: the current input, the previous hidden state, and the previous cell state. The current input is processed using a set of learnable weights, which are shared across all time steps. The previous hidden state and cell state are used to capture information from previous time steps and maintain a sense of memory. The output of the recurrent cell is a new hidden state, which is used to compute the output of the network. This process is repeated for each time step, allowing the network to process sequences of arbitrary length. RNNs are particularly well suited for applications such as natural language processing, speech recognition, and time series forecasting, where sequential data is prevalent. In natural language processing, RNNs can be used to model the sequential structure of language, allowing the network to capture complex patterns and relationships between words and phrases. In speech recognition, RNNs can be used to model the acoustic features of speech, allowing the network to recognize spoken words and phrases. In time series forecasting, RNNs can be used to model temporal relationships and patterns in data, allowing the network to make predictions about future values in a sequence. For example, an RNN can be trained on a sequence of stock prices to forecast future prices. One of the key benefits of RNNs is their ability to handle sequential data of varying lengths. This is in contrast to traditional feed-forward neural networks, which require fixed-length input sequences. RNNs can also be trained using backpropagation through time, which allows the network to learn from sequential data and adapt to changes in the input sequence. There are several variants of RNNs, including long short-term memory, LSTM, networks and gated recurrent units, GRUs. These variants were designed to address the vanishing gradient problem, which occurs when gradients used to update the network's weights become smaller as they are backpropagated through time. LSTMs and GRUs use specialized gates to control the flow of information and mitigate the vanishing gradient problem. In addition to their use in natural language processing, speech recognition, and time series forecasting, RNNs have been applied to a wide range of applications, including machine translation, sentiment analysis, and chatbots. In conclusion, RNNs are a powerful tool for processing and analyzing sequential data or temporal relationships. Their ability to capture complex patterns and relationships across time or sequence makes them an essential component of many deep learning systems. As the complexity and volume of sequential data continue to grow, the importance of RNNs in machine learning and artificial intelligence will only continue to increase.